Hello, my name is Virgil Kohlberg, and here is my Lab 3 on black holes. So for a little introduction, the purpose of the lab is going to be to use a computational simulation to find the mass of a black hole in the first step, and then find an initial velocity for a spacecraft to leave a planet and pass by a black hole without crashing in it or in the planet. So we'll have to find the initial velocity to leave a planet in orbit around a black hole. And we'll see that the results with the results through computational models, we'll be able to estimate both values, and we'll even have visual representation of the results. So here are a few concepts. First, we need to understand Newton's second law, that the force is related to acceleration. Force is also related to the change in momentum over the change of time, which is also known as the momentum principle. We also will need to understand the interactions between different bodies of non-zero masses, which is also called the gravitational force. Finally, when discussing circular forces and motions, we can talk about parallel and perpendicular components. The parallel component refers to the change in the speed, and the perpendicular component refers to the change in direction. They are both perpendicular to each other. The parallel one being in the direction of motion, and perpendicular one being perpendicular to that motion. So here are a few formulas and values. We can find here Newton's second law, force equals mass times acceleration, the momentum principle, change in momentum over change in time, the velocity update formula, the position update formula. Here, considering gravitational force, we can see that this is supposedly the gravitational force, even though there's missing a squared here. So please, my apologies, there should be a square. And here, this is the value of the gravitational constant. And we can see that the net force is equal to the parallel and the perpendicular forces. So for the first part of the experiment, we'll have to figure out the mass of a black hole. So the goal is to find the mass of the black hole, and the system is the orbiting star, and the surrounding acting on it is the black hole and its gravitational force. So here is the code. As we can see here, we have here we can find the change in momentum from the initial velocities. Then we can use that to find the net force acting on the star, and from the net force we can equate this to the gravitational force, because these two are the same forces, and through this we can find the mass of the black hole that we will calculate through here. So here are the results. So we get a lot of values at every timestamp of a potential mass of the black hole. But as we can see, we're not in exact circular orbit. So to find an average, I just had a new variable, sum mass equal to sum mass plus MBH, divided by the amount of, we'll say, values that were created. And our average that we find is 1.06128 times 10 to the power of 34 kilograms. So for the part 2, we had to find the escape velocity. So the goal is to find the velocity needed for a rocket to leave a planet in orbit around the black hole, pass by the black hole, and leave the system safely. So the system is the rocket, and the surroundings are the planet and the black hole acting on it. As we can see, there's the initial conditions here, the mass of the black hole that we previously found, the mass of the planet, the ship, timestamp, gravitational constant, etc. So here is the code that I've used. Here are the sum of the forces acting on the planet. So the force due to the black hole, and the forces due to the ship, and the forces of the ship acting on the ship, the forces of the black hole, and the force of the planet acting on it, that we can find here for the forces on the planet in the code, and the forces on the ship in the code. And here are the velocity and position update. So the results, we found that to reach a trajectory which comes close to the black hole but does not crash into it, we had an initial velocity of this initial velocity, which means that we're going drastically to the in the minus x direction and slightly in the positive x. Of course, this is all relative, because the initial speed is still of 35 million meters per second, which is huge, and the closest point to the event horizon is of 3.54 e to the 8 meters, so quite close. So in conclusion, the initial velocities can vary significantly and still achieve a working result. As we've seen, different values will have different, we'll say, impacts. We'll get closer or a bit farther. We'll have a more elliptical orbit, etc., etc. There's no one right answer. Additionally, the mass of the black hole may not be precise due to the length of time steps. We use time steps of 1 day, which is huge, which did impact slightly the results. And finally, the optimal velocity has yet to be determined, because I used trial and error to find these values, and we could calculate the perfect values in order to basically touch the event horizon without crashing into it. So as an extension, what does it mean? The difference between the parallel and perpendicular components of the net force and the change in momentum. Well, the net force acts instantaneously at all points. For the change in momentum over time does also the same thing, but there is there's always a slight lapse of time between those two values, and in a perfectly circular motion, it does create discrepancies. And also, it's usually way easier to use a change of momentum in order to find the force than vice versa. Finally, what if? So if we wanted to get orbit around the black hole, we can see that by increasing the velocity and speed, and decreasing, we'll say decreasing the magnitude of the x velocity, we will find an elliptical shape that will result in an elliptical trajectory around the black hole.